Okay, let's get started for today. We'll just be going over an intro to machine learning and some useful topics so you guys don't really have to, make sure to memorize any of the code or anything, just going over some topics and how this applies to astronomy as well. Okay, so first for some announcements. We did check-ins on this past Tuesday. If you weren't checked off yet, make sure to come to office hours this week. This, as well as the final project, is required to pass this class. So it's really important that you guys are checking in with us and we know that you guys have progress and know what you're doing for the next 2 weeks. And so final project presentations will be Tuesday and Thursday of the last week before Dead Week. So this is the last week of classes and this is right after Thanksgiving. Make sure to let us know as soon as possible if anyone in your group has time conflicts or can't show up to class that day. As of now, we're assuming that everyone can make both Tuesday and Thursday and that your whole group will be present in here at this classroom. Otherwise, if we know there's a few people with time conflicts, we can try to schedule a time maybe on Wednesday instead to do your presentation. And so lecture on Tuesday will be optional. It'll mostly just be project help. So all of the instructors that are still in Berkeley will be here and we can just help you out with anything you have related to your project. And it might also be a good time for your groups to meet up just to get some work done. Yeah, make sure to ask us for help if you need it. We still have office hours as usual, and we can help you out if you're just feeling confused on what you should do next in the project or if you're having issues debugging. And also let us know if maybe you're having issues communicating with certain group members. We can try to send them an email or just try to mediate that. Here's the attendance form for anyone on Zoom. Oh, and we also have, let me just show this. Okay, we also uploaded a file a few weeks ago. I don't know if you guys saw it yet. It's just like the formal document for the final project assignment. So it just mentions that everything that you'll need to turn in. The most part of your presentation is the actual presentation itself, as well as the presentation slides. And this is just a general guideline for what you want to put on your slides. The presentations themselves will be around 10 minutes. We require that everyone in the group speaks for at least part of it. Doesn't have to be for an equal amount of time, but just as long as everyone presents some part of the project. And we also require that you upload any code files and any videos or images that you're using for your presentation, as well as an individual write-up that you'll do, basically just summarizing, I think basically just a paragraph summary of things that you learned in the project and what you individually contributed as well. Yeah, so that's everything you'll need to turn in for the last week of class. Okay, so for an introduction to machine learning. Yes, question. Yes.
When we make our citations and references slide, we use a lot of background knowledge from this class. Would we cite like slides or lectures, or how would that work?
Yeah, no need to cite anything from the class. Mostly for the citations, we just want to know if you use a different website for inspiration on how to code something, how to structure something, definitely include that. Or if you looked at any research papers, but you definitely don't need to cite anything from this class. Or if you just looked up, oh, how do I write a for loop again? You don't need to cite any of that either. It's mostly for where you got your research sources and anything where you might have used some code from.
Okay, thanks.
Yeah. Does anyone else have any questions about logistics? Okay, cool. Okay, yeah, so as we've seen so far, I'm sure you guys have all experienced with coding your final projects, when we actually want to program anything about real life, it gets really complicated just because once you move away from really ideal equations, you start having to deal with all of these things in real life, such as maybe there's like some slight friction, air resistance, all of these things. And this is a lot to actually code in since a lot of these equations get really complicated. There's a lot of differential equations and stuff like that. And so the idea behind machine learning is instead of actually having to code all of these little equations for if we want something realistic, we can just let the computer learn through experience and rewards rather than have to code it ourselves to have the model complete a task. And so a lot of machine learning applications, you've seen a lot just in everyday life. So for example, self-driving cars, for the car to be able to detect, is this a pedestrian? Is this another car? That's a lot of machine learning on images. Even with Netflix and TikTok recommendations, it's a lot of machine learning algorithms to decide, oh, the user has swiped on this type of video really quickly. Next time, we should probably not give them that type of video as much. Even for languages such as Siri and Alexa, it's kind of impossible to write in code, this is what a voice sounds like. So a lot of this is also machine learning, giving a lot of data samples of people talking, and then kind of teaching these applications to infer things from voice samples. And so similarly with Google Translate between languages, and even for medical diagnoses, for looking at x-rays and stuff like that, a lot of that also requires machine learning. And also face recognition, like, Google Photos. No one's telling the computer, like, this is what a face, like, this is what, Emily's face looks like. Basically, they just train it on a bunch of images of yourself and then group them together. And so under the large umbrella of machine learning, there's kind of two large sub areas. One is supervised learning and one is unsupervised learning. And the difference between these two is basically whether or not you give the model that you're training on correct labels. And we'll go more into depth on each of those. Yeah, so basically supervised learning, you would give input data. So this could be any of your data such as voice samples, images, maybe even just points that you're plotting from data you collected, and labels. And what we mean by labels is, let's say you have a picture of a cow and you want your model to be able to detect and classify, is this a person or a cow? You would give a bunch of images, and then as your labels, you would say, this picture of a cow is a cow. Like this picture of a human is a human, just so the model can learn to distinguish between the two and assign different labels. And so we've already seen in class how to do regression. And so this is just fitting to any given data that you have. And this even includes basic linear regression, so just your y equals mx plus b. And so we've technically already done machine learning in this course from all of the SciPy optimize and all of the curve fitting. All of those are under the umbrella of machine learning. So we've already been learning about this in class. And then, as I mentioned before, classification. So if you wanted to classify, is this image a person or a car? This would also be supervised since you're giving them the correct labels and you're trying to get back more labels from your model. Yeah, and so then for unsupervised, the main difference is that you only give input data to your model and no labels. So for example, you have clustering. And so if you notice, like Netflix classifies movies as like irreverent thrillers, and you're kind of like this, like where are they getting this random label from? It's mostly because Netflix just does a lot of data analysis on the data and separates them into clusters. And then for each of these clusters, the model will then create common groups and also assign a label based off of common features. So here you're not necessarily telling the model exactly what you want out of it. It'll just be cluster it itself. And so going into more depth for regression, there's a lot of different types of models that as we've already seen in class. You have linear, polynomial, and also logistic regression. And the main idea behind this is that you just want to calculate parameters that minimize the loss. So the difference between the given labels and the predicted labels. And so we know that real data is never perfect and there will always be some errors and noise. And so this is always a trade-off that the model has to make between which points it wants to fit to and which points will be slightly off. And if you see below, it's also really important to think about simplicity versus overfitting. We can see that with the graph on the left. It's using a linear model and it's fitting pretty well, but you can see that the graph in the middle, which is polynomial, is a lot better. But at the same time, you don't want to keep going up in dimensions because this will just lead to overfitting. You can see the graph on the right, although it probably has the lowest error or loss out of all three graphs, it wouldn't be able to do well on data it hasn't seen before. And you would definitely want to pick the graph in the middle if you were going to fit your data to a model. And so there are a lot more other topics that go even more into depth on how you can avoid overfitting. You don't really need to know too much about these now, but some examples are just using regularization, cross-validation, or maybe choosing a different loss function. These are all ways to help avoid overfitting to your data. And so when we're using data, if we have a large set of data, a good way to avoid overfitting and to make sure you're actually understanding how well your model is doing is to split your data into a training set and a test set. And so basically you would use the training set of your data to actually train your model. And the test set would be to evaluate the accuracy of your model. And you wouldn't want to kind of combine these two because you want your test set to be completely separate so that you know how your data will do. How your model will do on data it's never seen before. And so that's why it's extremely important that your test set isn't also being used to train, since you don't want your model to overfit, and it might do 100% accuracy on the data that you're fitting it to, but then on a new point get it completely wrong. So in general, it's definitely more important to have high test accuracy rather than really high training accuracy. And so you can kind of see in this diagram, they've split the full data set into a training set and a test set. And then you can even further split your training set into a training set and a validation set, because a lot of times you don't have access to your test set necessarily. To all of you want to be able to adjust your model on your validation set before also using your test set as a final test. Okay, and then for the other type of supervised learning, we have classification. And so given many data points with different class labels, you want to be able to classify a new data point. So if you see like in the diagram below, if you have a bunch of data points, half of them are red, half of them are blue, you want to be able to predict, is this yellow point, like should it be part of the red group or the blue group? And so just from looking at it, we can kind of think, oh, it should probably be red since most of the points around it are red. But to formally have your model be able to predict this, you define a decision boundary to split the data. And so you can kind of train your model to then create this decision boundary. And you can see since the yellow point is to the right of this decision boundary, it'll classify the point as red. What do you mean by like random perturbation?
You randomly scatter the things around and then draw a arbitrary boundary.
Yes.
Most likely you wind up with more of one color than the other. And then if you were iterating the model as you have described it, you will wind up with essentially a bijection from an originally random distribution.
Yeah, so I think in this case, it does assume that there is a pattern that you can split on for your data. So I think you will have to change your model around a bit. Like given like what you know about the data. Yeah, you can see like in the next example, if your data is a lot more randomly scattered, you don't necessarily need like a linear decision boundary. A lot of times you can train your model to have kind of a more arbitrary boundary. And so with this, it's also really important to remember the trade-offs between having a small training error and getting high accuracy with your test data. So you can see the graph on the left correctly classifies every single point, but the graph on the right will be more general and will be able to classify points in the future much better. And you can see it still won't be entirely perfect just because there is a lot of overlap and the data isn't completely separable. Okay, and then another fundamental part of machine learning is neural networks. And so this is a really confusing topic. And basically, you can use layers of linear and nonlinear functions to model any other function. So if you see like in this diagram, you have your inputs of like different categories of like age, salary, education, and then these are all interconnected to nodes in the middle. And so all of these nodes will have, there basically be weights associated with them, similar to how in like SciPy Optimize, our weights are different parameters we want to find. And so the main difference between like a neural network and like SciPy Optimize, which we've seen before, is that this doesn't really follow any sort of equation. So it's not necessarily based on any physical equation that we know of. But basically, as long as you train your neural net on enough data and enough labels, it'll be able to adjust its weights so that it actually does really well. Yeah, and then finally, like the neural net will just have a final output similar to any other model. But it's kind of, you can think of it as a black box in the middle of, you can kind of construct a bunch of layers and it'll do a bunch of things, but we don't necessarily know as well as we do with like SciPy Optimize, like oh yeah, this was like the polynomial like equation that we put in, and those are the weights we're getting back. This is more of just like a black box. Okay, and so machine learning is extremely important in fields like astronomy and physics, especially now because astronomers need to use machine learning to modify and model and classify data. Whenever we use like the really large telescopes to go out and survey data, there's always a ton of data that like it would be impossible to go through everything one by one. Even when a telescope's just taking images at night, you can take hundreds and hundreds of images, and that would be too hard for a human to have to go through and look at each image. So some examples I have here are for like inferring stellar parameters from spectra. As you know, when like a star, based off of its emission spectra, you can kind of tell what elements are in the star. Similarly, with detecting supernova, this would be classification. You can use a lot of machine learning algorithms to help you classify an image as a supernova or maybe just a speck of dust. And also with spatial clustering of dark matter halos, a lot of machine learning applications can look at images and kind of cluster where these dark matter halos are. And so as you can see with spectra, you can kind of train your model on a bunch of spectra images with their labels. And then in the future, when you have new spectra, it'll be able to predict these. And with supernova, you can see image on the left and image on the right. The only difference is that the image on the right is a new image and has one small dot, which is a supernova. And so it's really helpful for being able to detect supernova. If you can make a pipeline to process these images, you can kind of see that if you have, like thousands of images from each night, and you have like a 3-month or a year and like 3-month difference, you can be able to use this and like automatically detect supernova without having to go through thousands and thousands of images yourself. Yeah, and we also have with galaxy type classification, you can similarly have a lot of images of galaxies with labels, and then create a classifier that'll be able to classify which type of galaxy it is. Okay, and so we weren't able to formally go into a lot of things. So here's some helpful links if you guys want to learn more. And a big recommendation I have for if you for learning more, it's really helpful to just look at some past lectures and assignments from courses at Berkeley, even if you don't have time to take them yourselves. So some courses that are really good and have intro to machine learning would be like Data 8, Data 100, CS 188 is about artificial intelligence, and you do a lot with neural nets as well. And if you want to be really hardcore, you can eventually take CS 189 on machine learning. Yeah, and I also believe Physics 188 also teaches an introduction to Bayesian and machine learning for physics and astronomy majors. So these are all really good resources to think about in the future if you want to learn more about this. Okay. Okay, and so for demo, I'll just show you guys some examples of neural nets and how you can use them to actually train things, just because it does seem a bit abstract, just kind of thinking about them. Okay, so for this example, this was a project to create a neural net that could then basically mimic a sine wave. And so you can see here as it's training, the weights keep adjusting so that it gets closer and closer to the model, to the approximation that you want to do. And so the neural net itself, though, is basically just a bunch of weights that will then approximate this sine function. And you can see that as it goes on, it slowly gets closer and closer to having lower loss, which you can see at the top that the loss kind of fluctuates a bit back and forth as it adjusts the weights, but in general, the loss is decreasing. And if you train it for long enough, it'll actually approximate a sine wave really well. Yeah, and then if you look at the code itself, it's basically just you have a bunch of layers and you have a bunch of weights, which are the W's here. And you can add a linear layer. You can use a nonlinear activation on your layer. Yeah, but it's basically just a series of linear and nonlinear regressions that all kind of add up to create a pretty good result. But if you actually looked at the weights themselves at the end, you wouldn't really be able to see anything resembling a sine wave there. But yeah. Okay, and then for another example, okay, so I recently did a project where we had to basically create a model that could classify the key points on a person's face from images. And so for this project, we trained the model on a training set of about 7,000 images, which is a lot. And so by the end of the model, you're able to then take any new image and be able to compute where the face points are. And so you can think, you can obviously see how this would be really helpful for applications like Google Photos, and just being able to maybe detect expressions and stuff like that. And so this was using a module called PyTorch, and this was all in Python. So basically through that, you can construct a model here. You can create a model and then add some layers. And then you can kind of train your model on the data repeatedly. You basically repeatedly train, pass in a bunch of input images with their labels to your model and then slowly update your weights. And so for here, you can see this is what the input data looked like. You can see the or this is what the training, while the model was training, this is what it was outputting. And so you can see that the green points are the labels and the red points are the predictions it made. And so you can see for different images, it does pretty well on the training set overall. The green points are pretty close to the red points. But then once you get to data that is not in the training set, so this was like for my test set, you can see it starts doing a lot worse because it hasn't seen these images before. And it still does a decent job, but definitely varies by image. So you can see that maybe some images where people are wearing glasses, or maybe they're smiling more with their teeth open, it doesn't do as well on. And so this took me about, I would say, I think the training part took at least like 10 hours to run, just my computer like on and like buzzing in the background. And then if I had more time, I definitely would have been able to train it on more data and for even longer to improve the accuracy of it overall. And so you can see here like the graph of the training and validation or test loss over time. The training loss slowly decreases, and the validation loss also decreases, but overall it's still much higher than your training error, just because the model hasn't seen that data before. And so for for a demo, you can kind of see here that it's just importing some libraries, but I'll try to use the net to predict some key points on the instructors' faces. So for here, I'm just loading in images of all the instructors and also just doing some pre-processing on the image to normalize the image and make it into a tensor. And then using PyTorch, I can load in a model that they have, and I can kind of change some of the layers around a little bit so that it'll be for our key points. And then here I just loaded the model I already trained for 8 hours, since obviously I wouldn't have time to train it right now. But you can see that if we run the model on the input images, so just the input images of the instructors, you can see that it'll guess where the key points of your face are. And you can see it does like decently, but not great. I think especially got really confused with James's glasses here. But yeah, you can see it does pretty decently. And so then I also had some code before. Yeah. And so you can see that this could be really useful. And so some other project that I did was morphing faces. So I took my neural net and put those points in, and then was like kind of tried to morph the faces. You can see this is me and James. It turned out okay. For reference, this is what like the face morph code will do on like if your points are really good and if you pick them by hand. This is like me and a friend, so you can see this is a lot better. So definitely like using a neural net was less accurate, but because I had 5 images, it was way faster to be able to do all 5 images into my net at once. Only took a few seconds to pick all the points, whereas when I did it by hand, just one image would take me like a minute or two to do. So it'd be like, if I want to do like 1,000 face morphs, I would definitely want to use my neural net, and results aren't as good, but still pretty good. We can see the other instructors. So this is James and Isla. So I think it actually looks pretty good. Isla and Elin, which is also a little scary. Yeah, and then you have Elin and Raph. So you can definitely see how just, after the 8 hours of training the neural net, but after that, it made everything a lot faster. And I was going to make these into a video too, but I kind of ran out of time to do that. But hopefully I'll, get that up and ready some other time. So that's it for the demo. Does anyone else have any questions? Yes. So in this case, a tensor would be like, I think kind of there's also physics tensors, and those are kind of basically like matrices you can learn more in like other classes. But and for this coding example, a tensor, you just need to convert like say a NumPy array to a tensor type, and so that it can work well with like PyTorch, the module that we're using to do all the machine learning on. But yeah, don't worry, you'll learn more in like upper division classes and more like math physics classes. Okay, yeah, and James also wanted to give some closing remarks, so I'll hand it over to him. Yes. Okay.
Can everybody like give a round of applause to Emily for machine learning? That was really cool. I think we looked really good. I think all the ones with my face probably looked the best, just saying. Anyway, so this is kind of like a soft close to our decal because, surprise, it's not really a lecture on Tuesday. It's like workshop to work on your projects, and we'll just be here. So this means this is kind of the last lecture, and I'm about to cry because I'm really sad. But I had to wish you all congratulations. Very nice, great success. So I just wanted to say a few things in closing remarks. Don't worry, we'll have a big shebang the week after Thanksgiving, but this is like a soft closing to the course. So I just want to recap what you've learned. You learned all the Python basics, so you know what a data type is. Hopefully you can recite them. If you can't, it's okay, I don't remember anything either. Functions, recursion, hopefully those words ring a bell. Conditionals, loops, object-oriented programming, etc. There's a lot of other things, but you learned all the basics in this class. You learned how to use external libraries for STEM. NumPy, SciPy, Pandas, Matplotlib, AstroPy, even a little bit of machine learning. We talked about PyTorch at the very end here. We didn't get to use it, but nonetheless, you've heard about it and you know what it is. You got to make some beautiful plots in Python, and you learned how to do that. We have that ultimate plotting guide. Consistently, people that have taken the course say they reference that thing every time they make a plot. So hopefully you will get a chance to use that after this course, but hopefully you have a bit of memory as to how to make nice plots. Since you all have taken the decal, I expect not to see a shitty plot from any of you. I want to see good plots in our department from now on. You learned how to do file IO. Like, yeah?
No promises.
Yeah. It's all good. It's all good. You know, beauty is in the eye beholder. But you learned how to do file IO. That's reading files in and out of your notebooks and your code. So now you know how to work with data files, CSV files. We talked a lot about that. Subplots. You know how to put multiple plots into one thing. I can't tell you how many times I've gone elsewhere to like other universities to do research, and I've met other undergrads that don't know how to put multiple plots on the same figure. That's a step ahead of the curve. You know what an IM show plot is? Plot real and model data, modifiers, curve fitting. Hell, you even know how to do animation. Technically, we've covered it, and you have the resources to look back at it, which is really, really valuable. And you know how to make a little bit of and use simulations. So we talked about numerical differentiation, numerical integration, root finding. We had a whole lecture on how to write a video game, which was pretty cool. And you did some professional development. You did an intro to research. We had a little bit of that. Rafi gave a great example of how to use real data. CVs, you learned, everybody in this class made a CV, curriculum vitae. You're ahead of the curve. A lot of people don't have those. You made your own personal professional website. That's very rare for undergrads. So boom, you are ahead of the curve in that sense. You know how to use LaTeX and Overleaf. You kind of know how to use GitHub. If you didn't really learn it that much, it's okay. It's a complicated thing. You get used to it when you use it more and more. But nonetheless, you know what it is, and you could probably pick it up if you wanted to on your own time, which is really, really valuable. So all these are just skills you have now. I should see a lot of this on your CVs someday. If I ever like come across you, hopefully maybe someday we're applying for the same thing or whatever. I don't even know. Maybe I'll be like something. I don't know. No, I hope to see your CVs and see them beautiful with all of these different skills you have access to now. That's a lot of knowledge. If you didn't get that meme, I'm sorry, you didn't have a culture back then. Anyway. So what's next? What's next for you? You have tons of opportunities now. And now that you know how to code in Python, like the world is your oyster in terms of astronomy and physics and other sciences. You can apply to research. So send a thoughtful, cold email to professors. Do not send like mass emails. I promise you they don't work. But you send a nice personalized email. Take the time to look into that person that you want to work with. Look at their archive and look at all the papers they've written. Try and find one that you really like and read it a little bit and try to ask questions. These are things that are really, really stand out for a cold email. I really encourage you to do that. If you find a professor or a postdoc in the science or in any department you want to work with, reach out to them. Python Decal is growing and growing in terms of notoriety in the departments, and I think professors really take it seriously now. So please don't let lack of experience stop you. You have the experience now. We highly encourage you to go to symposiums and colloquiums. You're ready for it now. You know the coding background. So if somebody asks you, can you make a plot? Everybody in this room should say yes, I hope. Every good cold email must be thoughtful and non-general. Read research papers, like I said, of the person you want to apply to work with. And then always don't forget to send like an academic summary or like an unofficial transcript. It's free to print out. Just go to Cal Central. And then link your CV and your personal website. It's a big flex. I promise you it'll help a lot, at least like in cold emails. You want to learn more coding? There's some great options for you. You could take Physics 77 or Physics 88. They're the same class. You honestly would be better off probably just taking Physics 88 because Physics 77 is just like 2 weeks of learning how to do Python, but you already know how to do that. Yeah,
I'm
it's
in that class right now, actually.
yeah. It's like they do like a crash course for like 2 weeks, and that's what makes it 77. And then people who are in 88 just jump in 3 weeks later, like assuming they know Python and they can do it. But yeah, and then Data 8 and Data 100 are also really good options if you want to just solidify your Python knowledge. Physics 188, when you like take a few more classes or you get closer towards the end of your degree, I recommend taking Physics 188. It's really cool. I'm not going to say anything about the way it's taught, but the homeworks are really cool. So those are really cool. Like you do machine learning. For example, my project the next 2 weeks is going to be to rediscover black holes merging with LIGO data. And then the one after that is to write a neural network that can distinguish images of galaxies between elliptical or spiral or bar galaxies just by using machine learning. So it's super cool. What else? Astro 128, that's the data lab. It's just really basically a lot more coding in really, really cool contexts. You get to make a lot of pretty plots. I really wanted to take it, but it wasn't offered when I was ready to take it, sadly. And then 61A, if you want some stupidly rigorous programming experience, I don't recommend it unless you absolutely really like coding. It's really hard. The tests are hard. It's fun, but hard. So if you want to get really, really good at understanding how a computer works, I recommend trying the 61A. Oh yeah, and then lastly, you can help teach the Python decal in the future. Everybody who's taking this class is eligible to do it. So we will talk about that more in a second, or in a hot minute. Class photo, just kidding. That's gonna be on Tuesday after the break. Not nearly enough people. There's like 50 of you in this class. So I wanna get as many people as possible for that photo. You don't have to take it if you don't want to, but I like reminiscing on like my class and like thinking about all the people that took it and bragging to my family during Christmas break or winter break. So we'll do that on Tuesday after break when everybody's here. Note about final projects. We're not going to tell you who goes first. We're not going to give that order. So everybody should come expecting to present on Tuesday unless you have like a super time constraint that you can't come. You can talk to us and we'll set a different day for you. But everybody else expect to be presenting on Tuesday possibly. So we should see the whole class here because you need your final project to pass the class. And it will be recorded. Whether or not you want to use that recording is totally up to you, but we'll record the whole class. We'll send it. You can take that, cut it to your section and post it on your website. It's a big flex. You have a presentation and put it on your CV. But class photos, again, will be Tuesday after break. So please come for that. Look your best if you want to. You don't have to. And you don't have to take the photo if you don't want to, but I would love it if you could. And then my last remark is course evaluations. So roast us, or not, but maybe roast us. It's anonymous, so you don't have to put your name. So it could be anonymous feedback. We want to know what you thought of this course, how it could be better, what you wish you saw, what you wish you wanted to see, whatever. Yes, just all the feedback. We want it all. And then intern applications. There was an announcement with both of these links. I sent it out like a day or two ago. Please click on that announcement. Both the links will be there. If you want to apply to be an intern, we'd love you to do that. We're not going to be here forever. Me, Isla, Emily, and Raf are all seniors. Sad. So we only have like 1 or 2 semesters left. So please, we would love to hand it off to people that we think could take over the course really well. Cool. That's all I have. Thank you everybody for coming, and good luck on your final projects. How are we on time? Yeah. Love the energy. Cool. So yeah, Tuesday or next week will just be workshop. So you don't have to come. There will be no attendance. Enjoy your Thanksgiving break. Use it, rest, and yeah, have a good one, everybody. I'm going to stop recording.
Woo! Thank you.
Yeah. Woo.